So, last time I showed you an experiment with a swing and a disc type magnet, and we discussed how the magnetic field lines change, or magnetic field changes its direction as you go around this magnet. Now, I will repeat the same experiment, but this time with another magnet, and that is this magnet, this ring magnet. It has a hole here, and then flat surfaces are the poles and all that. So, the same swing is here. Look at this swing, and I put this magnet here, and this horizontal part of the swing is above this gap, that hole in the ring, and similarly it is connected to the supply, and I will switch it on, and you see the direction of first deflection. So, it is going away from me, it is going away from me. Once again I am putting the power on and it goes away from me, and then I take this to a side. So, here let us say putting the power again, and it comes towards me, right. So, here also not only outside, but inside also the field lines are turning. So, the field at these places is definitely perpendicular to the surface and going away if this is north pole, but then it turns and changes its direction here, as it was the case with the disc magnet, and also it turns and goes into this hole. So, here also the field is opposite. Now, to further explore the change in the direction of magnetic field around this, I will do another experiment. So, here I have a compass here, you know compass, it has a magnetic needle, and the magnetic needle will settle in the direction of the magnetic field, generally used to find the direction north and south. Earth is a magnet, and from that magnet you have a magnetic field in south north direction, and if you just place the compass, the needle shows that okay, this is the north direction and that is the south direction, because the needle settles in the direction of the field. So, to explore the directions of field of a ring magnet, I will be just using this compass, and you see what happens, and from that you work out what kind of field is there because of this ring magnet. Okay, so here I have a small compass needle which is just fixed on some wooden stand that we have made, and then this is the ring magnet in vertical position, and this compass needle is almost on the axis of this magnet. So, I take it away from the axis, I have taken away from the axis. So, from here you look at the direction of that needle, and from that direction you have to find the variation of magnetic field direction near this ring magnet. So, now I am shifting it slowly towards the axis. You see how this needle of the compass is changing its direction, and from there infer how the direction of magnetic field changes parallel to the surface of the magnet. Okay. Once again going towards the axis, and then I will go away from the axis on the other side. Here I am on the axis, and again I am going away. So, this is how it changes. Now, let me do the same thing, but this time I am going closer to the magnet. So, let us see I am somewhere here, and then if I move away from the axis, see what happens. First, let me go left. It is like this. I am going towards the axis, and then from away from the axis. Do you see some change in the pattern? Let me go still closer. Okay, now I am shifting it towards the axis. See the pattern? Crossing the axis, and see how this needle makes two turns in between. Once again, see here it makes a turn, sudden turn, and then again it turns. Whereas, if I am slightly away from the magnet and then give this lateral displacement, you have very smooth turn. There are no sharp, sudden changes. So, you will have to explain how it happens. Now, let me move it towards this magnet and on the axis and see how that motion changes, what happens to this needle. So, where is the pointed end of this needle? Just watch, it is towards the magnet now, the broad end is away from the magnet. I am going towards the magnet on the axis, and you see it has started turning. See how it is turning? The compass is almost entering that hole of the ring magnet, and the needle has turned by almost 90 degrees. It is going into that gap, and see what is happening to this needle. And now what happens to the needle? All of a sudden it has turned by 180 degrees. Now the pointed end of the needle is away from the surface of this magnet. It has made a 180 degree turn. And what happens if I come back? If I come back, come outside, see what happens. See what happens. The pointed end is away from the magnet. Even if it is far away from the magnet, it is permanently changed its orientation. Once again I am repeating, this time the pointed end is away from the magnet and the broad end is towards the magnet, and I am going on the axis, almost on the axis, towards the magnet. So, my compass is going closer to the magnet, and you can see that it has started turning. The pointed end is away from the magnet towards my finger, and the broad end is towards this magnet, and see what happens, what happens, what happens, what happens, what happens, what happens, what happens. Here, 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 here. Here it makes the full turn, 180 degree rotation, and I am bringing it out. I am bringing it out, and the pointed end remains towards the magnet. So, both these observations, when I am shifting it laterally or I am shifting it along the axis, are to be understood in terms of the magnetic field directions of this ring magnet and how it acts on the compass and what happens to this compass needle when it is in a magnetic field and all those things. All right. So, on this df is equal to I dl cross b, I had shown several experiments in which a magnet produced magnetic field, and in that magnetic field we had currents. Now, I have a beautiful experiment on the same lines for the same equation, that this force df is I dl cross b, but this time it is a very special experiment because the magnetic field will not be outside the magnet, it will be inside the magnet. So, first enjoy the experiment and then we will do the explanation part. So, the apparatus I will be using is just a torch cell. I have just put it in this clamp stand so that I do not have to hold it. Here is the positive terminal of this cell and the negative terminal is here, and this is the wire. One end of the wire is taped with this negative end of the battery of this torch cell and the other end is free. Then I have a magnet, a strong magnet, cylindrical magnet, this is a small magnet. The flat faces are the poles, these flat faces are the poles. Then I have a screw, and this screw can just go and stick to the magnet. Just for decoration purpose, I put this paper clip here. This is also metallic clip made of iron, or at least part of it is iron. So, it just goes and sticks, and this whole thing can be stuck here close to this cell, torch cell. Here is the magnet which has magnetized this screw, and since this battery material also has some ferromagnetic things, it just goes and sticks there. So, what I am going to do is I will be connecting, I will be touching this free end of the wire to the curved surface of this magnet, and just see what happens when this circuit is completed. See how the magnet starts rotating. It is rotating so fast. Even after the circuit is broken, it takes long time to stop. Once again, so why does this magnet starts rotating? What you have is current. Current comes out of this positive terminal, say, it goes through the screw and then it enters this magnet, and from the surface of the magnet where this wire is touching, it goes to the wire and then back to the cell. But why the magnet starts rotating? For rotation you need a torque, you need a tangential force. Where is that force coming from? That force has to come from this df equal to I dl cross b, but where is that current and where is that magnetic field? The current is in this circuit, but I am looking for force on the magnet. So, the current should be somewhere in the magnet, and yes, the current is very much there in the magnet. It has to enter that flat space, and then from there it has to go down, and then it has to come towards the surface and reach this wire here, okay. So that current which is, or the say the component of current, although current is a scalar quantity, but still current has some component in this axial direction to reach the surface. It enters from top and it has to reach the surface. So it has to go in axial direction. That defines dl. That is the part of the current which is taking part in this whole experiment. So your dl is inside the magnet from the inner regions to the surface regions. That is dl, IdL. And where is B? The current I am talking of, that is inside the magnet from the central region of the magnet to the surface. So that current I am talking, and at that location you have magnetic field, and that magnetic field is the magnetic field which exists inside the magnet. So now what is happening? Your dl is actually out, and since the flat faces are here, so the magnetic field is vertical. So if you have dl vector like this and magnetic field vector like this, what will happen? Dl cross B. So there will be tangential force, and it is this tangential force which is actually providing the torque. All right. So this experiment is a very special experiment. It uses the magnetic field which exists inside the magnet. In all other experiments that we did, we used the magnetic field produced by magnet, but at outside points. Here we are probing the magnetic field that exists inside the magnet. You may be knowing this, that if you have a magnet, let us say this is north pole and this is south pole, your magnetic field here is, you can represent them through such field lines. But then all these field lines, they come back and enter the south pole, the south pole, and they do not terminate here, they go inside, they continue inside. Field lines are said to be continuous line, they do not originate from any point and they do not terminate at any point. So they continue inside the magnet. Field lines are always continuous, they never originate and they never terminate. So inside the magnet you do have magnetic field. Any line you start, it has to be a closed loop. Everything will be a closed loop. So it is this magnetic field inside the magnet, that we are using for this IdL cross B. So that B is provided by the magnet, inside it IdL is axial, and that gives the whole show. So this experiment that I showed you, we call it nail motor experiment, and motor is because we pass the current, we supply the current, and because of that it rotates. So anything that rotates in magnetic field when you supply a current can be called a motor. This is a very famous experiment, very popular experiment. At various websites you will see the description of this, because this is a very eye-catching. Another very eye-catching experiment is again very popular and available at many sites, and in school projects you will see this experiments at different places, and that is again a motor, and the construction is slightly different. This is anyway just a stand, homemade stand. We have these two copper plates fixed on some wooden frame, and you have two holes here, and these two copper plates are used to connect it to power supply. So, we have a power supply, and this power is given from here DC, and when I switch it on, you will have some voltages here. We take a copper coil, enameled wire, we made some few turns, not many turns, I can see only 5 turns or so, 6 turns. So, this is a enameled wire copper coil, and the ends of this wire are the enamel is removed at these ends, but in a very special way. I will talk about that later. So, we can put this enameled wire coil in this stand. The holes are made precisely to allow this coil to stay here like this. Okay. Now, we put a magnet close to this. So, this is the structure, this is the structure. So, what will happen if I put on the power? Current will come from positive, whichever side is positive, I believe the red one is positive. So, the current will come here, and then if the enamel is removed from here, it will go to this coil, and then depending on how the turns are made, it will go, current will go either this way or that way, and then finally it leaves at this terminal, this hole here, and then back to the negative of the supply. So, there will be a current in this. So, there will be current in this, and you have magnetic field. So, you have dl and you have B. So, you will have I dl cross B. So, there will be a force on the current. Of course, here it is not just one segment, the current is in this whole circular path, and on each part you will have that I dl cross B, and because of that force some motion will result. So, see what happens. I am switching the power on, and I just start it in the beginning. And it continues, the motor continues, current is being supplied by the power supply, magnetic field is supplied by this ring magnet, and force is supplied by my equation, dF is equal to I dl cross B, and from that the motion results according to Newton's laws. Okay. Let me put it off, and now there is a question. So, you can see that the coil is facing essentially this part of the magnet, this part of the magnet, this part of the magnet is quite far away for all positions of the coil. So, magnetic field is essentially from this part here. So, if the coil is in this position, essentially this is the part which experiences force, and when the coil goes here, essentially this is the part which experiences the force. Now, look at the direction of the current at this top part. Suppose the current enters from here and goes anticlockwise like this. So, here the current will be for me it is, let us say it is towards me, and here it is going away from me. When after half rotation this part comes here, current goes away from me, and when this part comes here, the current comes towards me, because current comes this way and then goes this way and then goes this way. So, every half turn the current direction opposite to this part of the magnet changes, but magnetic field does not change. the field direction is same, current direction is reversing. So if that happens, then dl cross b will change sign. So every half rotation, if the force is this way, after half rotation it will become this way. If that happens, then it cannot rotate continuously. So how do I manage this? What I have done so that it rotates continuously? Of course, I have not put the power on, that's why it's not rotating continuously. If I put the power on, yes, if I put the power on, then it will go continuously. So this is a question for you. You find out what we have done so that even though the current at the top should reverse, it gets the force in the same direction, it gets the kick in the same direction.